So today we're looking at section 2.3, and section 2.3 is about measures of central tendency. So a measure of central tendency is some value that gives an idea about the center of the data set, what's in the middle. And there are three different measures of central tendency that we're going to look at in this class. The first measure of central tendency that we're interested in is the mean of a data set. So we need to give a definition of the mean. The mean is the average of all the data values. So to find a mean, to find any kind of mean, you add up all the data values and divide by the total number of entries. So we have two different formulas for the mean, depending on whether we're talking about a population or a sample. For a population, we use the symbol mu. It looks like a fancy M. And that's going to equal capital sigma of x over capital N. Whenever we see that capital sigma, that's telling us to add. So this says add up all of your x's. The x's are the data values. And divide by n, which is the number of data entries in the population. So if you look back at our definition, the mean is the average of the data values. To find a mean, you add up all the data values and divide by the total number of entries. That's what this formula says, mu equals sigma x over n. It just says it in a formulaic way. The other formula for the mean is for a sample mean. And now instead of using the symbol mu, we use the symbol x bar. So x with a little bar on top is equal to sigma x over little n this time. So again, we're adding up all of the data values x and dividing by little n, which is the number of data entries in the sample. Why do we need a different symbol for the mean of a population and the mean of a sample? Well, oftentimes we'll be talking about both within the context of the same problem. We may use a sample mean to help us get an estimate for what the population mean should be. And if we're talking about both means within a problem, we wouldn't want to use the same symbol for both because that could be confusing. So whenever we're talking about a population mean, we use the Greek letter mu. Whenever we're talking about a sample mean, we use the x with the bar on top and call it x bar. So we have two notes here. The first note says Greek letters are always used for population values. So we'll be learning several different population values as we move forward, and those are going to use Greek letters as their symbols. The second note is that the mean does not have to be an element of the data set. So there's no rule that says if you find the mean of 100 numbers, that the value of the mean has to be one of those 100 numbers. As a matter of fact, frequently it isn't. It can be, but it doesn't have to be. So let's look at an example. Find the mean for this population data set. So we have 20 data values, 47, 31, 48, 56, 74, 105, 73, 99, 82, and 95, 51, 83, 29, 54, 89, 61, 97 and 106, 94 and 66. So those are our 20 data values that we're looking at. We want to find the mean. So the first thing we're going to do here, according to our definition, we see that sigma of x in our definition. That tells me I need to add up my data values. If I add up all 20 of these numbers, I end up getting 1,440. Then we want to divide by the total number of entries we had. There were 20 different numbers here. So to get our value for the mean, we're going to take the 1,440 and divide it by 20, and that gives us 72. So mu is equal to 72. How did I know it was mu and not x bar? Well, at the very beginning of this example problem, it said find the mean for this population data set. And when we talk about populations, we use the symbol mu. So mu is 72. We have another note. The mean can be greatly affected by outliers. So let's see an example of that. Here we have another data set. This time it says it's a sample data set. And we have 20 numbers in this sample. 27, 31, 36, 28, 32, 20, 25, 33, 32, 30, 32, 35, 33, 42, 26, 29, 27, 24, 28, 270. So those are my 20 data values, and we want to find the mean, but we're going to do it two different ways here. We have two things to consider. First, I want you to find the mean if you include the data value 270. And then in part B, I want you to exclude the data value 270 and find the mean. So when you look at these data values, they're all pretty much in the 20s, 30s, and there's one that's 42. And then all of a sudden, there's a data value that's 270. That value of 270 is most likely an outlier. So what I would like you to do is calculate the value of the mean if we include the outlier, and then calculate the value of the mean if we exclude the outlier. So let's take a look at the solution. First things first, we've got our data values, and if we include the value 270, that means we have 20 data values. So add them all up, they add up to 840. To find the mean, x bar, we divide the 840 by 20, and 840 divided by 20 is 42. Now if we exclude the 270, now when we add up the data values, they no longer add up to 840, they add up to 570. So when I go to calculate the mean, I only have 570, and now it's divided by 19, because since we excluded the value 270, there weren't 20 values, there were only 19. And if you do 570 divided by 19, you get 30. So if we include 270, the average is 42. If we exclude the 270, then the average is 30. So what does that mean? Well, if you think about it, when we excluded the 270, when 270 was not included, the average value was 30. And if you look at the data values, 30 seems like it's kind of in the middle of all of those that are in the 20s and 30s. 30 kind of seems to be in the center. But when we include the outlier of 270, suddenly the mean gets shifted all the way to 42. And 42 doesn't seem like it's in the middle of those data values. It seems like it's at the end, because most of those data values are in the 20s and 30s. 42 is the highest data value, not including the 270. So what you can see is that including this outlier pulled that mean up from being 30 all the way up to 42. It moved it towards the outlier. So we have another note. The mean will always be shifted in the direction of an outlier. So if you have an outlier that's on the far right side of the set, then the mean will move to the right of the data set. If you have a very small outlier, then that will shift the mean to the left in the data set on the number line. Next up, we have the median. What is the median? Well, the median is the actual central entry when all of the data values are arranged in ascending order. So in other words, if we put the data in order from smallest to largest, then when we find the entry in the middle, that's the median. There won't always be an entry in the middle. Sometimes there will be two. So we need to make sure we understand what to do in each case. If there are an odd number of data entries, then the median will be an actual value from the data set. If there are an even number of data entries, then the way we find the median is by taking the average of the two data values in the middle. If there's an odd number of data entries, there will be a single value in the middle. If there are an even number of data entries, you'll have to take the average of the two in the middle. So how do we find the median? Well, first thing we have to do is arrange our data set in ascending order. And once we've done that, we're either going to find our central entry, if there were an odd number of entries, or we're going to find the average of the two central entries, if there were an even number of data entries. So we have a note. The note says there will be the same number of entries above and below the median. So when you find the median on your number line and you look at all the other data values around it, there will be just as many data entries that are less than the median as there are above the median. So let's look at an example. So we have a data set, and this data set has 13 entries in it. 31, 47, 63, 51, 48, 59, 74, 82, 69, 32, 46, 52, 49. Those are our 13 data entries. So first things first, to find the median, we have to put this data set in order. So the smallest entry in this data set is 31. The next smallest is 32. After that, we get 46. Then we find 47 and 48. And then the next value is 49. And then 51. We follow that with 52. And then the next smallest value is 59. After that, we have 63. Then we have 69. Next, 74. And lastly, we have 82. So that is our data set in order. Because there is an odd number of entries, there are 13 data entries here, I'm going to go ahead and divide 13 by 2. I get 6.5. We're not interested in the and a half part. We're just interested in the 6 part. That tells me that I can go ahead and underline the 6 numbers to the left and underline the last 6 numbers in the set. And when I do that, you see that there's a single number that doesn't have an underline, and that's that 51. And that 51 is the median. So the median here is 51. Again, there are the exact same number of data entries below the median and above the median. How about another example? How about this data set? This data set is actually the same data set we were just looking at, only I added one extra value in. So now instead of having 13 data values, we have 14. Those values are 31, 47, 63, 51, 48, 59, 74, 82, 69, 32, 46, 52, 49, 46. Those are my 14 data entries. And we're going to find the median. Again, first things first, put the data set in order. We've already seen this data set in order. What is the extra value that we added here? There's an extra 46. In the first data set in the last example, in the data set that we had in the last example, there was a single 46. Now in this one, there are two 46s. So the correct order here is 31, 32, 46, 46, 47, 48, 49, 51, 52, 59, 63, 69, 74, 82. So now there are 14 data entries. If I divided 14 by 2, I get 7. I don't want to underline 7. I actually still want to underline 6, one less than that. That way I can see what's in the middle. So we have 6 entries on the left and 6 entries on the right underlined. That leaves the two values 49 and 51 in the middle. That's how we're going to find our median here, is by taking the average of those. So to find the average of 49 and 51, we add them together and divide by 2. And that's going to equal 50. So the median in this problem is 50. So we have another note. The median does not have to be an element of the data set. Now, if there are an odd number of data entries, it will be, because it will be the central entry. But it might not be an element of the data set if you have to find an average to get it, because it may be that the average of those two central entries is not a number in the data set. So that can happen. The next one that we're going to talk about is the mode. The last measure of central tendency is the mode. What is the mode? Well, the mode is the most frequently occurring data value. So basically, which number is in the set the most times? In the case that there's a tie between two entries, so there are two entries that are equally represented, maybe there's 5 each of those, then we call that set bimodal. So it's possible for a data set to have two modes. What if there's a tie between 3 or 4 or 5 different data entries? Well, then that's too many, and we say that the data set has no mode. So you can have a single mode, you might have 2 modes, or no mode. But you could never have 3 modes or 4. It's either 1, 2, or none in the case of the mode. So let's do an example. Consider this data set. We have 24 data entries here: 43, 48, 57, 61, 48, 52, 63, 57, 69, 52, 41, 45, 57, 68, 42, 51, 59, 57, 68, 42, 50, 42, 59, 72. And those are your 24 data entries. We want to find the mode. So to find the data entry that occurs most frequently, we can use one of our graphs to do that. And the best graph to find mode is the dot plot. So I'm going to go ahead and build a dot plot for this data. And here's what it would look like. You have a dot on the 41, 3 dots on 42, a dot on 43, a dot on 45, 2 dots on 48, a dot on 50, a dot on 51, 2 dots on 52, 4 dots on 57, 2 dots on 59, 1 dot on 61, 1 dot on 63, 2 dots on 68, 1 dot on 69, and 1 dot on 72. The mode will be the number that has the most dots, and that would end up being 57. 57 had 4 dots, and no other data entry had as many dots. So that dot plot is a good one. It can also help you find the median, because it can help you arrange the data set in order, which is necessary to find the median. Alrighty, so we have another note. The mode must be an element of the data set. It wouldn't make sense for it not to be, because the mode is the most frequently occurring data entry. So how could it not be in the data set? So let's take a look at a practice problem. We're going to find the mean, median, and mode for this sample data set. We have 30 data entries in this data set. We've got 15, 18, 22, 27, 27, 28, 29, 35, 35, 36, 36, 36, 39, 40, 40, 41, 42, 43, 44, 44, 44, 44, 44, 44, 51, 51, 51, 59, 67, and 68. Now, one thing you may notice is that I've given you this data set in order, and that is to reduce the amount of work you have to do. Since there's 3 different measures of central tendency you have to find, I thought I would be kind to you and put the data set in order. On an exam or on a quiz, you would have to order the data yourself. So give yourself a few minutes, pause the video, and when you're ready to see the answer, press play. Okay, let's take a look. We have our solution for the mean. We'll start there. We need to remember what these data entries were, all 30 of them. To find the mean, we're supposed to add them all up and divide by the total number of entries. If I add up these 30 numbers, they add up to 1,200. Then to find our mean, we're going to take that and divide by the total number of entries we had. There were 30 data entries. So our mean is x bar, because we were told it was a sample. X bar equals sigma x over little n, which is 1,200 over 30. And 1,200 divided by 30 is 40. So the mean of this data set is 40. For the median, we need these data values in order, which they already are. And we need to find the 2 in the middle. So the 2 data entries in the middle are going to be the 40 and the 41. We add those together. 40 plus 41 is 81. And we divide that by 2. 81 divided by 2 is 40.5. So our median here is 40.5. Now, putting the data set in order will also help you find the mode, because it makes it clear how many times something occurs. And in this case, the most frequently occurring data value is going to be the 44. There's 6 of them there, and there's not 6 of any other data entry. So our mode is 44. So you should be able to do all 3 of those measures of central tendency. What else is in this section? Well, another important concept is the weighted mean. So not just a regular mean, but a weighted mean. What's the difference? Well, in a weighted mean, that's where you're finding the mean of a data set whose entries have varying weights. And it's found by taking x bar and setting it equal to the sum of each data value times its weight divided by the sum of the weights. So x's are your data entries, w's are the weights of those data entries. Where would you ever encounter a situation where some of the data values mattered more than others? And the answer is this class right here, and a lot of your classes. So this is the type of mean that you're using in your classes where different grade categories make up different portions of your total overall final grade. So for instance, in our class, exams are worth 70% of your entire grade. That means the exams are weighed more heavily than the homework. Homework is only worth 15% of your final grade. So it has less weight. So that's what we're talking about when we're talking about weight. We're talking about which data values have more impact on the overall value. Let's see an example where we use this. You're taking an English class, and there are 4 different grading categories. Exams are 60%, quizzes are 20%, homework is worth 10%, and you have a term paper that's due that's worth 10% of your final grade. At the end of the semester, you ended up with these percentages. So for your exams, you had an average of 82%. For your quizzes, you averaged only 65%. On your homework, you got 90%. And for a term paper, you got 72% on the term paper. So how are we going to use these scores along with the category weights to determine our overall grade? And the answer is we're going to expand this table. So to compute our final grade, we're going to expand the table. And what we're going to add in is we're going to add in the categories along with their percentages, but then we also need to incorporate the weights. The weights of the exams were 60%, for the quizzes it was 20%, for the homework it was 10%, for the term paper it was 10%. Notice I've put the weights in decimal form. It's a good idea to put one of these two in decimal form. Don't put them both in, it makes it unnecessarily difficult. You can leave one in percent form and put the weight as a decimal. And now what the formula says is we're supposed to multiply each data value times its weight. So for exams, we're going to multiply 82 times 0.6. And 82 times 0.6 is 49.2. Then I'm going to take the quiz percentage, 65, and multiply it by the weight, 0.2. 65 times 0.2 is 13. Then we do the same with the homework. 90% times 0.1 is 9%. And for the term paper, 72% times 0.1 is 7.2%. Then what the formula says is I'm supposed to add the x times w's and add the w's. So if I add up the weights, those add up to 1. If I add up the x times w's, those add up to 78.4. So that my final average x bar is the sum of x times w divided by the sum of w, which is 78.4 divided by 1. And so that's 78.4%. And so your overall grade at the end would be a C. Now that's assuming that your teacher is using the standard grading scale where 90% and above is an A, 80% to 89% is a B, and so on. So we can use this same process that we just used on the classes categories to compute a GPA for somebody who's taking classes in college where the different classes have different numbers of units. In other words, if you're taking a PE class that's worth 1 unit or 2 units, and this stats class that's worth 4 units, the stats class has more impact on your grade point average than the PE class does because it has more units. It has a heavier weight. So let's see how that process would look. So let's say you're taking 5 courses: biology, statistics, English, poli-sci, and PE. And your results are listed in the table below. We want to compute the GPA. So in your biology course, you got a B at the end of the semester, and the course was worth 5 units. In stats, you got an A, because of course you're going to work hard in stats, and it was a 4-unit class. Your English class was a 3-unit class, and you got a C. Your poli-sci class was a 3-unit class, and you got a C. And your PE class was a 1-unit class, and you got a C. So we want to figure out what the GPA is going to be. So to do that, we need numbers for those grades. And those numbers, you may remember, are an A is worth 4 points. That's why we say that somebody who has straight A's has a 4.0. So A's are worth 4 points, B's are worth 3 points, C's are 2 points, D's are 1 point, and an F would be worth 0 points. So now we can expand the table. Those grades are going to be our X's, and the units are going to be the weights. So now we're going to take the number value for each grade and multiply it by the weight. So for the biology grade, we take the grade of 3 and multiply it to the units 5 and get 15. Stats grade is a 4 times units, which is 4, gives us 16. 2 times 3 gives us 6. Another 2 times 3 gives us 6. And then for PE, 2 times 1 gives us 2. We have to add up the weights and we have to add up the x times the weights. So when we add up the weights, we see that we were taking 16 units this semester. When we add up the x times w's add up to 45. We're going to use our formula that says take the sum of the x times w's and divide by the sum of the w's, which is 45 divided by 16, and 45 divided by 16 is 2.8125. That would be your GPA for this semester. So one thing that occurs, especially when you're reading through studies, is that there's a lot of data there, or it might be that you don't see the data. All you see are the conclusions and the frequency distributions, but you never have access to the original data because it could be thousands and thousands of data values, and so they don't print that with the study. Well, then how would you know if the mean that they're reporting to you for that particular data set is accurate or not? And what you could do is we could actually use the frequency distribution in the study to find a mean from that frequency distribution. Now it's an approximation, right? It's going to be close to what the value of the mean for the actual data set would be, but it's not guaranteed to be exactly the same. But if you do this process and you find the mean of the frequency distribution, and it's very close to the mean for the data set, then you would think that it's a pretty good approximation. So let's see how that works. It's called the mean of a frequency distribution. The mean of a frequency distribution is actually a weighted mean, so it's just like what we just got finished doing. We're going to use the class midpoints as the x values, and we're going to use the class frequency as the weight values. So we needed a value for the data point itself, and if we have a range of values, the best value we can use is the value right in the middle, which would be the midpoint. And so we have this formula, x bar equals the sum of x times f over the sum of f. Hopefully you can see how similar this is to the weighted mean formula that said that the mean x bar was sigma of x times w divided by sigma of w. Now all we've done is we've replaced the w for weights with f for frequency, because the frequency is the weight. So let's test this out in an example. Find the mean of this frequency distribution. So we have a class from 28 to 40 with a frequency of 57, from 41 to 53, frequency of 89, from 54 to 66 with a frequency of 113, from 67 to 79 with a frequency of 78, from 80 to 92 with a frequency of 60, and from 93 to 105 with a frequency of 21. But again, we don't have the data values, we just have the distribution. So let's go ahead and find the mean. I'm going to expand the table to also include midpoints, because the midpoints of the classes are going to be my data values, and I need to incorporate a column for multiplying each one of the original midpoints times the frequencies. So the midpoint of the first class from 28 to 40 is going to be 34, because if you add them together, 28 plus 40 is 68, divided by 2 is 34. How do we find each successive midpoint? Well, we could do the same thing, add the two endpoints together and divide by 2, or we could just find the class width. In this problem, the class width is 13. Remember that class width is always equal to the difference between consecutive lower class limits. So the first lower class limit was 28, and the second lower class limit was 41. So that means that the difference between 41 and 28 is the class width, and that's 13. So we can take our first midpoint of 34 and add 13. We get 47. Add 13 again, 60. Add 13, we get 73. Then 86. And then 99. So those are our midpoints. Now we're going to take each one of those, because those are our x values, and we're going to multiply them to the weights, which are our frequencies. So 34 times 57 is 1,938. 47 times 89 is 4,183. 60 times 113 is 6,780. 73 times 78 is 5,694. 86 times 60 is 5,160. And 99 times 21 is 2,079. So that gets all of our values. Now we can apply our formula. We have to add up the sum of the f's, just like we had to add up the sum of the w's before. When we add up the total frequency, we get 418. And then we have to add up the x times w's, each data value times its weight. And when I multiply these and add, I get 25,834. So now we're ready to find our approximate value of the mean. X bar is going to equal the sum of x times f divided by the sum of f, which is 25,834 divided by 418, which is 61.804 when we round to 3 decimals. And so that is our mean. The mean here is 61.804. So remember that this 61.804 is just an approximation. If we actually had access to the data values, we would want the true mean. We'd want to go and use those data values to find the mean. But if we don't have access to those data values, this is the next best thing. So we would compare this to the mean that they stated, and if it was close, then we would tend to believe that that mean was calculated correctly. So next, we want to talk about the shape of distributions. When we look at histograms for our frequency distributions, the histograms can resemble lots of different things, but there are some basic shapes of the distributions that we want to be familiar with. We're going to discuss 4 of those distribution shapes now: the uniform distribution, the symmetric distribution, the skewed left distribution, and the skewed right distribution. So we'll start by talking about the uniform distribution. In a uniform distribution, you'll notice that all the classes have approximately the same frequency. When you look at this graph, the bars aren't exactly the same height, but they're very, very close. We would always expect some slight variations when we're accumulating data, but for data to be dispersed like this, that means there has to be some kind of underlying pattern in the background that's generating this uniformity across the histogram. When we have a uniform distribution, then there's no mode. Since all the bars have the same height pretty much, there's not one that's really higher than the other ones, but the mean is equal to the median in the uniform distribution. In a symmetric distribution, there's symmetry. We can think of drawing a vertical line right down the middle, and the left and the right sides are approximately mirror images of one another. When we have that situation, then the mean is equal to the median, which is equal to the mode. So our 3 measures of central tendency are equal to each other in a symmetric distribution like this. Then we have our skewed distributions. We'll start with the skewed left distribution. What makes it skewed left? Well, that means there's a tail on the distribution that goes off to the left. So it gets longer and thinner out to the left, but it kind of stops abruptly on the right-hand side. In a skewed left distribution, the mean is always less than the median, and the median is always less than the mode. So the mean is less than the median, which is less than the mode. A skewed right distribution is similar. The only difference is it has a tail that extends to the right. And when this distribution happens, then that means that the mean is greater than the median, which is greater than the mode. So you can always put those in order, mean, median, and mode, on a skewed distribution. You'll always know where to find those. We have another note. The mean always lies on the tail side of the median. So if you have a skewed distribution, either skewed left or skewed right, the mean is going to be farther to the tail side than the median will be. So you can always, if you have two values that you're comparing, you can always know which one's the mean and which one's the median, because the mean will be farther towards the tail. Alrighty. So we have a practice problem dealing with the mean of a frequency distribution. I want you to take this frequency distribution, where from 31 to 39 we have a frequency of 30, 40 to 48 it's 57, 49 to 57 frequency is 72, 58 to 66 has a frequency of 41, 67 to 75 has a frequency of 36, 76 to 84 has a frequency of 13. And find the mean. So you'll have to find the midpoints, multiply by the frequencies, and follow the formula. You'll need a few minutes to do that, so go ahead and press pause on the video, and when you're ready to see what the answer looks like, press play. Okay, so let's take a look at the solution. We're going to expand the table to find the midpoints. We've got our classes and our frequencies. The midpoint of the class from 31 to 39 is 35. Now, if we figure out the class width, we can use that to generate the rest of the midpoints. The first class begins at 31, the second class begins at 40, so 40 minus 31 is 9. That's the class width. So we take the 35 and we add 9, we get 44, add 9, we get 53, add 9, 62, add 9, 71, add 9, 80. So now we have our midpoints, and we're going to multiply each midpoint times the frequency. So 30 times 35 is 1050, 44 times 57 is 2508, 53 times 72 is 3816, 62 times 41 is 2542, 71 times 36 is 2556, and 80 times 13 is 1040. We're supposed to add up the frequencies. They add up to 249. We add up the x times f's, which add up to 13,512. Then we follow our formula that says that x bar is the sum of x times f divided by the sum of f, which means it's 13,512 divided by 249, which gives us an approximate mean of 54.265. So our mean here, x bar, is 54.265. That's our mean. That brings us to an end of section 2.3. Make sure to look on Pearson for your homework, and have a great day.